In this video, I'm going to cover the math behind the quantitative comparison between packet and circuit switching. There are two fundamental approaches to move data through a network of links and switches. In circuit switching, the resources needed along a path to provide communication between 2 points are reserved for the duration of the communication session. In packet switching, these resources are not reserved. A message is broken into packets and sent through different links until they reach the destination. One question that rises when choosing when to use packet or circuit switching is, which one is more efficient? Or, in other words, which one allows more users? Well, I'll use ENCE to represent the number of users in circuit switching and NPS to represent the number of users in packet switching, and I will start by defining some information about this simple network. The users will share a link with a capacity of 1 megabits per second, and each user, when transmitting information, will generate data at the rate of 100 kbits per second. Users are transmitting only 10% of the time. With circuit switching, 100 kbits per second must be reserved for each user at all times. If we divide the shared link capacity by the bandwidth required by each user, the circuit switched link can support up to 10 simultaneous users. With packet switching, the way to get the maximum number of users that can share the link is addressed slightly different. And this is because the link is now shared among users and they are active only a certain percentage of time. We're going to ask the following question. What is the probability to have more than 10 users, any one among 35, that are transmitting and the remaining users are not transmitting? So the number 10 comes because we're comparing with the circuit switching, so let's see if we can handle more than 10. And 35 is a random number. We can substitute later by any other number that makes sense to analyze or use. We're dealing with a probability question. Let's dive in. We'll start by finding the probability of one user to transmit, which is equal to 0.1%. We can also find the probability of n users to transmit, the probability of one user to transmit and another user to transmit and another user to transmit. Notice that we have the AND operator, which corresponds to a multiplication, and we get p to the power of n users transmitting. Now we'll find the probability of that other user not transmitting. By using the rule of subtraction, I get 0.9, so 1 minus 0.1. We can also find the probability of all other users that are not transmitting. If we do that, we get this probability, 1 minus p to the power of the number of users minus the number of users transmitting. In summary, we have an individual probability for one user transmit and one other user not transmitting, and we have the generic probability for n users transmitting and all other users not transmitting. I'm going to keep those probabilities in the top corner because they are going to be useful in a minute. And now I'm going to ask a different question. What is the probability to have one specific user transmitting and the remaining users not transmitting? Looking carefully, we are applying the rule of multiplication. Let's map that rule to what we know. And the probability that event A, one user transmitting, times the probability of event B, all other users not transmitting, is given by the multiplication of my generic equations. If we plug some numbers for one specific user transmitting and other users not transmitting, the probability is 0.2 278%. But what if instead of one specific user, we want any other user transmitting among the 35 and the remaining users not transmitting? In this case, we need to find a way to select samples. There are two possible ways to select samples. The first one, permutations, where order matters, and the second one, combinations, where order does not matter. In this particular case, it does not matter the order of the user that is transmitting, so we're going to select the users using combinations. The expression for the number of combinations is the following. Combining all the information that we know together, we use combinations to select any one user among the 35 users, and we multiply by the probability of that event happen. The result of this multiplication is what it's called a binomial distribution. We represent the binomial distribution in the following manner. N is the number of users transmitting, NPS is the total number of users, and P is the probability of success of N, the number of users transmitting. We'll see later why it's called a binomial distribution. Plugging some numbers, and we observe that the probability increased to 9.7%. No surprise here, due to the fact that we no longer have just one specific user transmitting, but we have anyone among the 35 that can transmit. Let's revisit the original question. What is the probability to have more than 10 users, anyone among the 35 transmitting, and the remaining users not transmitting? If I rephrase these, what I'm trying to say is, what is the probability that there are 11 or more simultaneous active users? Notice that I'm using the OR operator, which implies an addition. Let's use the binomial distribution equation that we learned, and we want the probability of 11 or 12 or 13 or so forth and so on up to 35 active users. And if we compute the summation of all those binomial distributions from 11 to 35, we get the probability of 0.04% active users transmitting. For this particular example, notice that the probability of having more than 10 users simultaneously active is very small. That makes packet switching, packet switching provides essentially the same performance as circuit switching, but it does that allowing for more than 3 times the number of users. Let's cover now why this multiplication here, it's called a binomial distribution. We have in this piece of paper all the information that we need. We have the maximum number of users, 35. We have the number of users that are transmitting, which it's equal to 10 or any other number that you want to find the binomial distribution, and the probability of 0.1 or 10%. I also have here the result of the binomial distribution when we have one active user among the 35 transmitting, which is 9.7, and hopefully we get the same answer. And now let's use Desmos to plot this information and see if we get the binomial distributions. So if you open Desmos, we are going to start by defining our NPS, which is equal to 35 users. The number of users, I'm going to put 1 for now, and the probability equals to 0.1. Let's find the binomial distribution, which is given by the number of combinations, which is this part here in blue. So let's compute this one first. Going back to Desmos, what we have is NPS factorial divided by n factorial times NPS minus n factorial. This times the probability of having those guys transmitting times all the other ones that are not transmitting, and you get the probability of 9.7%. So we get the same answer. We're getting these 9.7%. Cool. So now let's plot and let's see how do we get this graph over here. So let's go back to Desmos and let's create an array here of 1 user to 35 users, or let's say, sorry, NPS users. So it goes up to 35. And let's create, the result is going to be another array of those elements. So I'm going to copy this because it's the same expression, and now I'm going from element to element. So I equals to 1, I equals to 2, I equals to 3, and I get an array of elements. And let's plot this, so and see what we get here. Let's adjust the axis. I'm going to the x-axis and I go from 0 to 35 and the y 0 to 0.3. We can zoom out if we want. All right, pretty cool. Now what we can do is, it seems like that it's not a binomial distribution here, but if I move my probability, I can start seeing the probability moving around. That's pretty cool, huh? Another thing that we can do is, this n does not make much sense because this n is not influencing the graph, it's just influencing the calculation of just one individual value. But I can increase this NPS. So let me go and increase my x-axis to, let's say, 200 nodes. And now I go here and let's say that I have 135. Well, let's put 100 for now. And you can see the probability changing, also the distribution, or even this. If I change, you can see the probability also getting affected by the number of users that I have available to transmit. Pretty cool. Play around with it and have fun.